So very good morning to all. So we have completed the first chapter regarding the various types of state space representations and the solution of state space equations. Also the state transition matrix. So, state transition matrix is having some properties and also having some significance in the state space analysis. So you have to identify those two, okay? Properties as well as significance. In the second chapter is about analysis and design. Analysis and design. So we have started the second chapter in the last class, and the first concept. These are the concepts, the PPT, the slide you are looking at. All the concepts in the second chapter I have compiled in this slide. So first we will see the controllability and observability. So controllability and observability. What is controllability? What is observability? How to comment on controllability and observability? I have given you in the last class. Okay. We can comment on controllability. We can comment on controllability by inspection, or we can calculate it, or we can use a method called controllability through controllability matrix, similarly observability through observability. These two we have completed. And I asked you to find out, are there any other methods to find out the controllability or observability? Are there any other methods? Next, principle of duality, and next, concept of state feedback. Concept of state feedback. So these are the topics. Effect of state feedback, pole placement through the state feedback. The last three topics are related to state feedback. Okay. What is state feedback and what is important, I will tell you later. Principle of duality we have completed in the first chapter itself. Okay. It is nothing but the duality between controllability and observability. I have given you the basic idea of controllability and observability and finding the controllability and observability using controllability matrix and observability matrix. We have seen the real meaning of controllability. We can access the state variables. We can access the state variables. Madam, B4 ever, madam. Who is B4? B4 is
and this is disabled chain, sir, for participants.
So who is roll number B4? I have removed him. So ఇక్కడ ఎవరు రాస్తున్నారో క్లియర్గా తెలిసిపోద్దండి. So if he wants to attend my next class, he have to give the explanation. Madam B4 again waiting room లో కూర్చోండి మేడం. అలో చేయొద్దు మేడం.
Yes, sir. Yes, sir. Yes, sir.
Some of you told him he has to join only after giving explanation. So let us see the topics. Okay. We are looking at controllability and observability. And we have seen what is the meaning of controllability and observability in the last class, and then the method of identifying whether the system is controllable or not through the controllability matrix. So today let us see the second concept, that is controllability through Jordan canonical. Controllability and observability through Jordan canonical. Jordan canonical form is a subcase of parallel form. Okay, when there are repeated groups, we can say that if we represent it in state space, we will not get pure diagonal matrix. We will get Jordan blocks in which the off diagonal matrix elements are not equal, and we will get ones. We have gone through. It happens when there are repeated poles there in the system, or repeated eigenvalues there in the system. Let us see this. So when state space representation is in parallel form, it is very easy to identify. And the system diagonal matrix are distinct, or eigenvalues are distinct. It is very easy to comment on controllability or observability by the equations are perfectly decoupled. What should we do there? Simply observe the elements of matrix. Simply observe the elements of matrix. This representation is in diagonal representation, that is parallel representation. It is pure diagonal matrix. All the remaining elements are zeros. If you observe the matrix B, if all the elements are non-zeros, then the system is controllable. See here. This is also diagonal matrix. This is also parallel representation. But here one of the element of matrix B, that is input matrix, it is 0. It means the state corresponding to this element, that is first state x1, first state corresponding to this element, we cannot control through the input. That is the meaning. Then we can say that system is not controllable. System is not controllable. This we have seen in the last class. See here, one more example I am considering. This is also represented in the parallel form only, but here what is the difference? Here the Roots are repeated. Roots are repeated. There is a -1 root. It is repeated. So we will get a Jordan block like this. A Jordan block. This is off-diagonal element. This we will get as one. And this particular block, these two are same. This particular block is called Jordan. Here the idea is we have to treat this particular Jordan block as a single element. Okay? This is one element. These two zeros as second element. These two as third element, and this is as fourth element. Okay, even though the matrix is 3 by 3 matrix, now we are assuming it as a 2 by 2 matrix. Why? Because of this Jordan block, we will consider it as a single element. That is the idea. Next slide. See, when state space representation is in parallel form and there are repeated poles or eigenvalues, we get Jordan canonical form. We get Jordan canonical form. Here we should consider Jordan block as single element. The rows of the matrix P corresponding to the last row of Jordan block should not be all zeros for the system to be controlled. So this is the Jordan block. It means this is the block corresponding to the repeated root. What is the repeated root? -1. Okay. For these two blocks, blocks, what is the two elements corresponding to input matrix? These are the two elements corresponding to input matrix. What this statement is saying is the last row of Jordan block the last row of matrix P. Okay? The last row of matrix P corresponding to Jordan block. This is the Jordan block. These are the two rows corresponding to Jordan block. Among these two rows, which is the last row? This is the last row. This is the last row. Since there is only one input, we are getting only one element in that row. Otherwise, we will get as many number of inputs. So what that point is saying, we should not get all zeros in this particular row. All zeros in this particular row. If we get all zeros in this particular row, then the system is not controllable. If we get not all zeros in this particular row, then the system is controllable. That is something. Okay. Next, one more condition is the elements of each row of the matrix P corresponding to distinct Jordan blocks, should not be all zeros. Should not be all zeros. So what is this point? I will tell you after considering some more difficult example which contain two Jordan blocks. Here, how many Jordan blocks we are having? Only one Jordan block. In some cases, there are two or more repeated rows. Then we will get more Jordan blocks. See this. So carefully observe. So these two are distinct eigenvalues. No term is 0. So it is parallel form only. or equations are decoupled, then the system is controllable. Then the system is controllable. Coming to here, this is the Jordan block. This is the Jordan block. And these two are the rows corresponding to Jordan block. Rows corresponding to Jordan block. The last row elements must not be zeros. Here the last row is having an element 4. It means the system is controllable. The system is controllable. See here, this is what I told. Here it is having two Jordan blocks, -2 and -5. Two repeated rows are there. Two repeated rows are there. This is one Jordan block, and this is another Jordan block. What I told you, we should consider all the Jordan blocks as a single element. So this is one element. All these zeros are second element. This is third element, and this is fourth element. So even though it is 1, 2, 3, 4, 5, 5 by 5 matrix, because of two repeated rows, all the rows or order of this entire matrix we should treat as 2 by 2. Now observe your point. The last row. This is the last row. It is having two inputs. It is having two inputs. Last row corresponding to first Jordan block, and this is the last row corresponding to second Jordan block. Last row corresponding to second. So what is the point saying? It should not have all zeros. It should not have all zeros. Okay, how many elements are there? Two elements. One is non-negative. Okay, how many elements are there here? Two are non-zeros. Okay, if both are zeros, then the system is both are supposed. Instead of 3, here if it is 0, instead of 3, here if it is 0, then the system is not controllable. Since here there is a element 3 is there, and this row is a non-zero row, this is also non-zero row corresponding to Jordan block last row. Here the system is controllable. What is one more point? This point. So the element of each row of the matrix is corresponding to distinct Jordan. The elements of, what is this meaning? I will explain. See here. This is the first row. The second row. This is the third row. 3 rows are corresponding to this Jordan. Observe the 3 rows. Observe the 3 rows and connect this with this particular point. The elements of each row of the matrix B corresponding to distinct Jordan block should not be all zeros. I will explain the second point in a moment. Just wait. The same thing holds good for observability also. The same thing holds good for observability also. How I will tell you. So before observability, let us see some non-controllable examples. Non-controllable. See, this is the fifth order system having two repeated roots -2 and -5. Okay. Here you see the last row corresponding to first repeated root is non-zero, but the last row corresponding to second repeated root is 0. Second repeated root is 0. So hence the system is not controllable. System is not controllable. See here also. These are also the systems which are not controllable. This is the Jordan block. And the last row corresponding to the Jordan block. These are the two rows corresponding to Jordan block. The last row corresponding to Jordan block is having all zeros. The system is not controllable again. Similarly, observability also. So what is observability again? In case of the system is completely represented in what you call diagonal canonical form or parallel canonical form, it is very easy to comment on observability. How? Just observe the output matrix. I told you already, observability, whenever you speak of observability, we will observe output matrix. Whenever we speak about controllability, we will speak input matrix. So the output matrix, if it is having all non-zero elements, then it is observable. If any zero is there, then the system becomes unobservable. Okay. Same explanation holds good for observability as well. There the rows, here the zeros. So what should we do when the system is represented in Jordan canonical form? That is, in the system is having repeated roots or repeated poles or repeated eigenvalues. Here we should consider Jordan block as a single element. All the explanation is same. Jordan block as a single element, and the columns, there the rows, here the columns of the matrix C corresponding to first row of the Jordan block. Here last row, here first row. First row of the Jordan block should not be all zeros for the system to be observable. Similarly, the second thing, the elements of each column of the matrix C corresponding to distinct Jordan block should not be all zeros. So we will understand this again through the example. See, these are the systems which are observable. These are the systems which are observable. So let us go through the conditions. So this is the Jordan block. And this is the column corresponding to first row of Jordan block. This is the first row of Jordan block, and this is a column corresponding to first row of Jordan block. Since it is a non-zero column, then the system is observable. Then the system is observable. Similarly, the next is here. Here also the system is observable. How many Jordan blocks are there here? There are 2 Jordan blocks. This is one, and this is one more Jordan block. So this is the first column corresponding to first row of first Jordan block. This is the first column corresponding to first row of first Jordan block. Second Jordan block. Okay? So first row of second Jordan block. If you see these two are non-zero. Okay? Non-zero columns. So the system is completely observable. Here the examples of non-observable. Examples of non-observable systems. See, this is the Jordan block. The first column corresponding to first row of Jordan block is zeros. This is also first Jordan block, second Jordan block. First column of first Jordan block is non-zero. It is perfect. Okay, but observe the second Jordan block, first column. Okay, this is the second Jordan block. Corresponding to this Jordan block, in the output matrix, the first column will be this. This is having zeros. This is having zeros. So this is the first row. First column. This is having zeros. So it means the system is unobservable. So very easy. Only thing is you should first know what is Jordan representation. Jordan representation, you should have a clear idea. This is there in your syllabus. Okay. This is not only the method to find or to comment on controllability and observability. There are many methods that are available. The best method is that we have discussed yesterday, that is controllability through controllability matrix. But controllability and observability identifying through the Jordan block is clearly mentioned in your syllabus. That is why we have taken these examples. These are well explained in textbook. So you please go through these examples also. Why? Because these are clearly mentioned in the syllabus, so you may get questioned, especially if you give commenting on controllability and observability through Jordan representation. Okay. Let us come to the next topic, that is state feedback. What is state feedback? So before understanding what is state feedback, first let us know the importance of design in this state space representation. Like we design in transfer function analysis, we will design a controller to improve the transient response or steady state response. Okay, a suitable controller will be designed according to the requirement. So here also we shall design suitable controller. What is the idea there? I think you might have studied it here. So we will find out the new pole's location according to the new requirement of design, either in transient response or in steady state response. Suppose I want to reduce the rise time or I want to reduce the steady state error. What should we do? We will immediately calculate the new poles corresponding to the new requirement. Okay? And the task is the original poles to be shifted to the new location. Okay, original poles to be shifted to the northeast, shifted to the new location. That is the idea here. So how to do this we have seen through the root locus and Bode flag. I think I have taken for the B section control systems last time in the second year. I have explained this. Okay? How to shift the poles to the new locations with the help of root locus and Bode flag. That is in transfer function analysis. Here we should do the same thing here, that is shifting the poles to the desired locations or new locations, but we should do it in state space analysis. For that we will use the concept is called state feedback concept. State feedback concept. So let us see what is state feedback. Okay, so the idea is for an nth order system, we should inject n adjustable parameters in the system, so that these n adjustable parameters make the changes in the system so that the poles will be shifted to the new locations or desired locations. So we are going to introduce these n adjustable parameters through the state feedback concept. Here what we do, instead of output we will feedback the state variables itself. We will feedback the state variables itself. So we will feedback the state variables through the feedback gains, and we will finally calculate these gains. And so by considering an example, we will better understand this. We will take up the example in this class, but as of now, let us see the idea. Okay, this is the block diagram representation or plant representation. Okay, generally in transfer function, what we do, we will feedback the output to the input. But here in state feedback, what we will do, instead of output, we will feedback the state to the input, through the state feedback. Observe carefully, it is very important. Okay? In regular control systems or transfer function analysis, what we do, we will feedback the output to the input. And don't confuse with this. This is not feedback. That is the part of state representation. That is part of state representation. That is not the feedback. Generally, what we will do, we will feedback the output to the input. But what we will do here the state to the input, through the state feedback. If you understand this, then the rest of the things are very easy. The same thing is explained with respect to signal flow graph when the system is represented in phase variable form. So remember this point also, phase variable form. So state feedback will be an easy process when the system is represented in phase variable form. I think you have remember what is phase variable form. That is the first form of the state space representation. The very first format of phase variable. Okay, where the output and its n-1 corresponding derivatives or successive derivatives as we consider as state variables. Output will be considered as first state variable and its n-1 derivatives as second, the remaining state variables. Okay. So this is the sectional flow graph representation without state feedback. This is after state feedback. This is after state feedback. So we will see this concept completely with the help of an example in the next class. Thank you. And that person B4, he has to give me an explanation personally. Otherwise, I won't allow him for the next classes. Madam,
Sir.
closing.